This video is about optical aberrations, a review for LensCrafters doctors. When I was at the clarifye training, I realized that a lot of doctors forgot what optical aberrations were. This video is just to review optical aberrations, and hopefully you will find this helpful. So quickly, just to review basic optics, there's something called avergence, which is just a curvature of the wavefront. So here is an example of avergence. It's called avergence, and it's just a curvature of a wavefront. And the way you find avergence is just 1 over r, 1 over the radius. So for example, if you have an object that's 1 meter away, you will have 1 diopter, 1 divided by 1 in air. So the avergence of this black curve will be 1 diopter if the object is 1 meter away. Now this concept of avergence is very powerful, as you can calculate the object avergence, the image's avergence, and find out the image location, if it's a real or virtual image. You can find out the lateral magnification of the image compared to the object. This is very powerful. However, in real life, there's aberrations. There's optical aberrations. It doesn't match this avergence relationship. And the reason being because of the peripheral rays. The avergence relationship only applies to rays around the optical axis, parallaxal rays. So for example, let me move this over. For example, rays number 2, rays number 3, rays number 4. Those are parallaxal rays. Rays on the periphery, rays number 1, rays number 5, are called peripheral rays, non-axial rays. And because of that, you have aberrations. You have aberrations because the angle of incidence is much larger in the peripheral rays than it is in the parallaxal rays. Because of that, you have optical aberrations. By the way, this figure is from Geometrical and Visual Optics from Dr. Schwartz. Geometric and Visual Optics by Stephen A. Schwartz, PhD. So just know that you have optical aberrations because of peripheral rays away from the visual axis. So there's 5 types of classical aberrations, Sedell or classical aberrations, right here. There's spherical aberrations, coma, oblique astigmatism, curvature field, and distortion. These are called classical aberrations, Sedell or classical aberrations. When you have a lot of aberrations, there's really nothing you can do unless you send it into a lab to be specially made, wavefront guided eyeglasses. If you have a lot of coma, there's really nothing you can do. However, if you have a lot of spherical aberrations can manifest at, it's called night myopia. So the reason being because in spherical aberration, the peripheral rays refract more than the parallaxal rays, the central rays you see here, and because of that you can develop night myopia. This is from the same book, night myopia from spherical aberrations, because at night the pupil dilates, exposing the retina to the peripheral rays. So when the pupil dilates, the retina gets exposed to these rays. Oh, maybe do it in black. These rays over here, and you develop night myopia. So let me show you a patient that I had. So this is the daytime pupil from the clarifye aberrometer, and this is the nighttime pupil. You can see a lot of spherical aberrations, and you can see the auto-refraction at night and the auto-refraction in the daytime, and you can see that there's a significant amount of night myopia. I actually did a night refraction on this patient, and he preferred more minus at night. I gave him a separate prescription at night to drive at night because he had a lot of spherical aberrations at night, and it actually manifests as night myopia. So look out if you see a lot of spherical aberration, then it can manifest as night myopia. It doesn't happen all the time, but it should happen most of the time. So that's one thing you can treat is the spherical aberrations. With the coma, with the trefoil, with secondary astigmatism, you can't really do anything unless you get the wave-fronted guided eyeglasses. If you're wondering what these numbers were, these aberrations are from the aberrometer. It's not from classical aberrations. It's different from classical aberrations. So the Z number is called the Zernike polynomial. And it describes the shape of the wavefront that exits the aberrometer. So it's different from the classical aberration. So I'll have a figure from the same book. Let me show you the figure. So they're here comparing the Zernike polynomial to the classical aberrations, the Seidel aberration. And second order, number two in the Zernike polynomial is just defocus. Third order is comparable to the coma, and fourth order is comparable to the spheroidal aberrations. Alright, that's it. Hopefully this helps, and that's it.